Hello everyone. Welcome to this TA session on optimization methods for civil engineering. So this course will be taught by Professor Rajiv Kumar Bhattacharya of IIT Guwahati. I'll be one of the TAs of this course. So this is kind of as part of my PMRF Research Fellow program. So I'll be conducting a TA session at every Sunday from 3 to 4 p.m. So this is kind of a pilot experiment with some week zero assignment questions that I'll be going through today. So before going into the details of this course, you will find it in the course website that you need to have some prerequisite related to linear algebra calculus or basic level class 12 level linear algebra and calculus or basic engineering level that you have learned in your first or second year in engineering mathematics. And then you'll be able to get to this course and you'll find comfortable to carry on with this course. And you will from this course you will learn many aspects of real life problems, maybe not necessarily only related to civil engineering problems or planning problems, but you will be able to take up real life problems and take up those challenges and you will be able to solve those. So, to give an introduction of myself, so I am a second year PhD student in Indian Institute of Science. I'm Rita Bratanath, and so I'll be suggesting all of you to attend this TA sessions live from week one itself. And as I have mentioned, it will be conducted from Sundays 3 to 4 p.m. So during these sessions, I'll mostly have it an interactive session where you will be able to ask your doubts, but not necessarily doubts related to your assignments. I'll be solving some similar problems that will be there in your assignments, but you cannot directly ask questions from the assignment. So if you have any doubts related to the concepts of the weekly class related to that, then I'll be probably able to answer those queries. And also, the main focus will be obviously to solve some problems during the sessions. So do attend it live because in that way you'll be able to grasp things better. And also, these videos will be available in YouTube, so you can go through these videos later as well. But I won't suggest you to do that, and it's beneficial only to attend it live. So, without further delay, I'll start with the class of this week. So it's a week zero content where you will, if you log into your profile and go to this course page, and you will probably see that there is some week zero assignments that's been given. That's kind of a prerequisites. So as I mentioned, all those problems will be related to whatever you have learned already. So just look at them carefully and try to solve them. And I'll be solving some of those questions and relevant questions in this session. And do come with questions if you have during the next TA sessions related to that. I'll probably be able to answer that. So without further delay, so let's proceed. So first question that I'll like to solve is that you know some of the concepts of maxima and minima that you have learned in basic class 12. So how you minimize a function of one variable. So it's like suppose this problem is related to minimization or maximization of a function of single variable. So in this course, we'll dive deep into multivariable optimization, but first you need to have this knowledge of this basics. So suppose I take a function uh, fx, which is 3x to the power 4 minus 20x cubed plus 36x squared minus 20. Suppose I want to uh, minimize, or like suppose I tell you that this function has maximum at p and minimum at x equals to q. So find p and q. So this is your question. So how would you proceed to solve this? So let me write down the function again. So what you have learned from your class 12 mathematics is that you can use simple calculus like derivatives. You can take the first or second derivatives and can test whether a maxima occurs at some point or a minima occurs at some other point. So there is this first order necessary condition which you have, which is, I'll write it down, first order necessary condition. So now you take the derivative of this function with respect to x, and you will get 12x cubed minus 60x squared plus 72x. Now, if you set this function to 0, then you will find some solutions to this function, and we call those solutions as the stationary points. So let us do that. Suppose we set it to 0. Then what you will get, you can get 12 will be cancelled out and x will also come out. So it's like x squared minus 5x plus 6 equals to 0. So it's like x times x minus 2 times x minus 3 equals to 0. So from this, you will have three solutions for x. One is 0, other is 2, and another is 3. So these are called the stationary points. Now you need to know whether a maximum or a minimum occurs at one of these points. So let us try and test that if you can. So there is another concept called the second order condition. So let us take the second derivative of this function with respect to x, and you will get 36x squared minus 120x plus 72. So here again, you can have, say, 12 will come out probably, yeah, 12 will going there. So it's 6x squared minus 10x. Uh, sorry, it's not 6, it should be 3. So it's 3x squared minus 10x plus 6. So now what you can do, you have to check uh, the signs of the second derivative when you put this stationary points. So suppose I write down a concept which you can have. If x naught is a stationary point of fx, and if double prime x naught is greater than 0, that will imply that x naught is the minimum point. On the other hand, if you have if double prime x naught less than 0, then it will tell you that x naught is the maximum point. And if you have if double prime x naught equals to 0. So this is not conclusive. There might be a point of inflection or a maximum or a minimum. You need to go for higher derivative tests. So now let us look at this function. So it had 0, 2, and 3 as the stationary points. So suppose if I put f double prime 0, it will give you 12 multiplied by 6, that's 72. So this is a minimum point. If f double prime 2, if you put this, you will get 12 times 3, 2 square, 10 plus 6. So this part is 12 plus 6, 18, and this is minus 20. So this will be less than 0. And if you put f double prime 3, you will get 12 into 3, 3 square, minus 10 multiplied by 3 plus 6. So this part will again be positive. So here, this qualifies as a minimum point. This will again qualify as a minimum point, and this will qualify as a maximum point. So if you look at this function, it has two minima and one maxima. So a function can have multiple minima or a multiple maxima, and these will be called the local minimum or local maximum. And if you find out the minimum or the maximum over all these local minimums or local maximums, you will have the global minimum or the global maximum. So now let us test this. So we have this function. Let me write it down again. Fx is 3x to the power 4 minus 20 x cubed plus 36 x square minus 20. Hope I have write it down properly. Let me just check it once. Yeah. So this was the function. And now if you put f0, you will get probably minus 20. If you put your f3, you will get so this will again be like 243 or something, this first part. That's 3 to the power 5. Uh, I hope I have done it correctly. Yeah, I think so. And this will be 540. And this will be 36 multiplied by 9. It will be 324 and minus 20. So if you add this up, it will be minus 560, and this portion will be like 5, uh, 6, 7, something like that. Yeah, and this will be minus 560. So this will be 7. So this qualifies as a global minimum here. And if you put f2, you will get the maximum of this function. Let me zoom out a bit. So your f2 will be something like cube plus 36 2 square minus 20. So this will be 16 multiplied by 3, that's 48. This will be 8, 160. This will be 36 multiplied by 4, something like 144, and this is minus 20. To add this 2 up, it will be 192 minus 180 or something. So this is 12. So this 12 is indeed the maximum value of this function. And this is the global one as well. So this is all about the first question. So it might happen that you will solve this problem and you will get f double prime x naught equals to 0. So in that case, you can go for higher derivative test and check whether it's indeed a maximum or a minimum, or it is called an inflection point. So I'll explain the second question related to this. So suppose I give you a function fx and I tell you that this function has a f prime a equals to 0. So at x equals to a, it takes this first derivative takes a value 0. So you can certainly say that stationary point is a. So it could be like one of the stationary point. So one of the stationary points is a. Now suppose I give you that f double prime a equals to 0. Now can you say, what can you say about a, whether it is a maximum or a minimum or it's something else? So suppose let's work with some examples to understand this better. Suppose I give you this function fx equals to x to the power 4. Now, if we take the first derivative, it gives you 4x cube equals to 0. And if you want to find out the stationary point, so that will essentially give you x equals to 0 as the stationary point. So here, a equals to 0. So it's like a is 0 here. Now, take the second derivative. What do you have here? You will have 12x squared. So f double prime of 0 is also 0. So you cannot say anything whether it's a maxima or a minima or anything else. So what do? You take the third derivative. That's 6x. And again, you will find that it is 0. Finally, you take the fourth derivative. I'll write it as 4. And that will give you 6. And that's greater than 0. Even if you look at the function, you can see that since it has an even power, if you put x equals to 0, that will give you a minimum. So this function cannot take a negative value. It will always take a positive value or it will take a value of 0. So it's kind of a similar argument of what we had before. There we had first derivative equals to 0 and second derivative is greater than 0, implying a minimum. Here it will also imply a minimum. But here, if you look at closely, you will see that if you have your highest order derivative as 0, which is the third derivative, which is the odd derivative, okay, third derivative, highest order here, uh, sorry, let me erase this, write it. Highest order, which is taking a value 0 at x equals to 0. And this is an odd order, you can say. And then the next even order, so this is an even order, and it is taking a positive value. So this 6 is positive, this is positive value. So this will imply a minimum point. So this is kind of your example 1. Now let us take another example to understand this problem a little bit better. So let's take example 2. So in this example, what you have, suppose your fx now is x cube. So now what can you say about this function having a maximum or minimum or something like that? So let's take the first derivative. This is 3x squared, you set it to 0 and you will get x equals to 0. Then f double prime x is 6x, and again f double prime 0 is 0. Then you take the third derivative and it will give you a value of 6 and it's greater than 0. But now the highest order, which is 0, is even order. Now what can you do? Suppose you look at this function of x equals to x cube. You know that f0 is 0, and you know that if say 0.01, which is 0.01 cube, is a positive. So you can put a very small number here, and then you have minus 0.01 cube. So this is an odd power, and this will be less than 0. So your graph will be something like, so in the positive region, you will have uh, like positive increment, and in this side, and here you will have a negative increment. So this point will be a point of inflection. So x equals to 0 is a point of inflection. So this will imply that on either side of the function, you will have one increasing portion and another decreasing portion. So this is how you can solve this kind of problem. So let me move to the third problem of this problem set, or the assignment that we'll be discussing. So right now we have learned the basics of calculus. Now what we can do is that we need to know something about linear algebra in this course as well. So I think many of you have learned linear algebra in your bachelor's year in your college. And let me refresh your memories with one example of a problem related to eigenvalues. So this is the third problem that I'll be solving today. So let us take a matrix A, which I can write as 1, 2, minus 3, say 4, 1, 5, and 0, minus 2, and minus 3, something like this. So find the product of the eigenvalues of A. So this is the question. Now, many of you might have gone through this problem already, but let me tell you the basics of it. So, when you need to solve this kind of a problem, what you have to do, you have to use a determinant. So now, determinant of A minus lambda I equals to 0, and if you solve for lambda for this problem, you will get the eigenvalues. So where I is the identity matrix of order 3, and your lambdas are the eigenvalues. So you'll probably have 3 roots for this equation, and you will have 3 eigenvalues, and you will need to find the product of eigenvalues. So one crude way of doing it is like evaluate all the eigenvalues and then take the product of it. But you don't do it in that way. So the best possible way is that you need to know that determinant of A equals to the product of the eigenvalues. So this is a property. So you can prove this property. I think it's pretty basic. You can get it in any engineering mathematics book. So I'm not going into this session. So let me just show you the problem solving technique just now. So now you take the determinant. So I hope my screen is visible. Yeah. So 1, 2 minus 3, 4, 1, 5, 0 minus 2 minus 3. Now you take the determinant. So it's pretty basic now. It's 1 multiplied by minus 3 plus 10. Then you will have, if you expand this in terms of this 4, so you will have minus 4. You delete this, so it's minus 6, minus of 6, something like that, as simple as that. So you will have 7 from this portion, and this evaluates to minus 12, then it's plus 48, and it's 55. So that will be your answer. So that will be your product of the eigenvalue. So it's pretty simple, and you can solve it using this technique. Hope I have done the calculations right. You will just double check it, and I think it's pretty simple. You need to know the expansion of this determinant, and that's all. So let me talk about something more about this problem. So you can have similar kind of expression if you just expand this determinant with a minus lambda I, and you will get 3 roots from that. And there is technique of getting 3 multiplication of the roots of a equation. So from that you can also solve it. Another common question that is being asked is the sum of this eigenvalues. So let me ask, what is the sum of the eigenvalues? So in order to solve that problem, what you can do is that let me talk about, yeah, so sum of the eigenvalues will be the trace of the matrix. So if you know the trace, so trace of A, so trace is nothing but the summation of the diagonal elements of the matrix. So you pick 1, 1 and minus 3, you add, sorry about that, you add them up and you will get minus 1. So that's your sum of the eigenvalues. So without solving this problem, actually, you can get the sum of the eigenvalues and the product of the eigenvalues. So you will encounter many of the linear algebra concepts in this course. So like to ask you to just refresh your memories before this course gets started. And I think you'll be able to solve problems related to this quite easily in that case. So I don't think I want to discuss anything more related to this. So let me go to the next problem, which is problem 4 for today's class. So as I have already mentioned, I have gone through this calculus problem, one linear algebra problem. Then there can be another problem which is related to civil engineering. So uh, who doesn't like to solve problems related to shear force and bending moments and all those things? So I think as the structure folks might like this problem, and yeah, if you have learned civil engineering, it's quite basic that you have already solved problems like this one. So let me draw a simply supported beam, and then you will have a triangular loading here. So this is your W, which is your triangular load that's been coming over this simply supported beam. So the question is to find, so suppose I name it as point A and this is point B and the length of this is L. Find the distance, find the point or the distance from support A where the maximum bending, sorry, it's not bending, yeah, bending moment occurs. Now, how do you solve this kind of a problem? So let me go through this step by step. First, let me draw this again. So let me just draw a triangle here, that is simpler. Yeah. So you have this simply supported beam. This is point A, this is point B, this is distance L. This is your W. Now, from this point, you have to find where the maximum bending moment occurs. Now, the first step, if I name it as force 1, this is F2, F1 and F2. So find F1 and F2. So this is not an optimization as such because you have already learned this. So yeah, my screen is probably now visible. Yeah, I think it was appeared a little bit late after I wrote it. Anyway, so let's solve this. So this point A can be named as 0, 0 coordinate. This point B can be named as L0 coordinate. And this can be again some L comma W coordinate. So this force will act from say a point, this equivalent force, which will be at a distance L by 3 from that point. So that equivalent force is nothing but half times W times L. So that's WL by 2 that's acting at a distance L by 3 from support B. So that's our first step done. Now let's move on to the second step. Okay, write this down again. Second step. So my second step will be to now take a section at a distance say x from supporting. And let me just name this height as y here. So your y by x from the properties of triangle you can have equals to w by l, and your y is nothing but wx by l. Now, or I'm sorry, you still haven't found the f1 and f2, so let me erase this and I'll come back to this again. So now you will have a couple of equations that you have to write. So one is that your f1 and f2 will balance this load. So f1 plus f2 will be wl by 2, and you will let's take the moment of forces with respect to, say, point A here, sorry, point B. So that will give you F1 times L minus your WL by 2, and it's acting at a distance L by 3 from 3, it's equals to 0. Now if you solve this, just eliminate L from here, you will be left with F1 is WL by 6. And if you subtract from the earlier equation, you will get F2 as WL by 3. So yeah, so I think this is correct. 6, 3, yeah, this is correct. So now you can go to the second step. So this was our first step. Now I have already taken a section at a distance x. So I have already mentioned to all of you that by properties of triangle, y by x equals to w by l, and you will have y equals to wx by l. And now, if you just look at this section, again the equivalent force will act at a distance x by 3 from this section. So now the equivalent force here for that section is nothing but half times wx by L times x. So that's wx square by 2L. Now, you know where it acts, and now if you take the moment, so now you take the moment with respect to the section, we'll get F1 times your x minus this equivalent force, and that will be at x by 3. Yeah, so that will be F1x minus wx cubed by 6L. So let us name this as a function of x. Now we have to maximize this function. Maximizing this moment means maximizing this function. So now we can see that again this is a function of a single variable, which is x. So we can adopt the similar approach that I have talked about before, and then you can solve this. So let me take the first derivative with respect to x here. That will give you f1 minus 3wx square by 6l. So let me set it to 0 to get the stationary point. So that will be your, suppose 3wx square 6l equals to f1. F1 is nothing but your WL by 6. So you can eliminate your W's and 6 from here. So you'll be left with 3x square by L. And so you have eliminated W by 6. So it's L. So x square is nothing but L square divided by 3. And your x is nothing but L by root 3. So this is where your maximum bending moment should occur, but you still need to do the second derivative test. So now if you take the f double prime x equals, then f1 does not contain anything with respect to x, so that's 0. Then it's minus 3w by 6l times 2x. So this 6 and 6 will be cancelled out. You will be left with Wx by L. So obviously this is less than 0 because X, L, and W's all are positive here. Pardon me for that. Okay. So this is essentially tells you that X equals to L by root 3 is the maximum point of fx. So this is where the maximum bending moment occurs, and this is a distance from support. So let me just check it once again. I had taken, yeah, this, I took it from the supporting. So that's not a problem. So this is how you can solve problems related to civil engineering also, like structures. And again, you can see that this portion, I have used the concept of the second step of stationary points and the maxima and minima. So you can see that this is kind of directly relevant to what you will be studying in this course. So this is the simple one variable example. So probably you have a multivariable kind of an objective function, like, and then there will be some constraint like physical constraints, and then you have to optimize something to have a solution to a social problem, something like this. So that's essentially will be the goal of this course. So I think you will get to know more of those applications when you take this course, and be like going through this course, like after a few weeks, you'll be able to grasp it better. So now I have solved the fourth problem. So I think I'll be solving some two more problems today, and then I'll be calling it a day. So since this is not a live session, not a live session here, so I don't have an option for interactions with the students. But during my live sessions, I'll be having some interactions with the students. I'll probably be asking some small questions whenever I'll be solving these problems. And also, I want to plan to keep some 10 minutes at the end so that you can ask your doubts as well. So I'll be stopping at say 50 minutes, and then I'll be taking questions for the rest of the 10 minutes. That will be the goal of my TS sessions from next week onwards. So since I still have some 15-minute time in this 1 hour session, so let me solve two more problems. So now I have already told you the concepts of say linear algebra, calculus, then this civil engineering concepts like structures. You still need to know, you still need to have some idea on the graphs as well. So let me give an example. So this is the fifth problem, and you'll probably find a similar problem in your assignment of week 0. So now suppose I have a line, say 2x plus y equals, or sorry, let me put it as greater than, equals to 2. So suppose this is your line 1. And then suppose you have another line, which you call it as line 2, and you have this equation as x minus y, say less than equals to 3. Now what you have to do, uh, you need to draw the feasible region bounded by this line, and then probably I'll add some more lines and ask you how to like draw the feasible region of that part as well. So essentially this can be a linear constraints in your say your of your optimization problem. So within this region, x and y can lie, and then probably you have some objective function that you need to maximize. So more of this you will be learning in your linear programming chapter, a linear programming class that sir will be taking. So let me give an idea. So now, if you draw this figure, say this is your x-axis and this is your y-axis, and now you have some y prime here, and here you have some x prime. Now you have this 2x plus y greater than equals to 2. So this line will pass through if you put y equals to 0, x equals to say 1, and another will be y equals to 2, something like this. Your line will be something like this. Need to extend it. So pardon me for my bad drawing. So this is a straight line. So this is your line 1. And then you have another equation, which is x minus y less than equals to 3. So suppose then your x will be 3, so it will be somewhere here, and your y will be minus 3, it will be somewhere here. So let me just draw the line first. Yeah, so just erase it. I'll be erasing it later. So this is your, say, line 2. Now, let me name this. This is 3, 0. This is your 1, 0. This is your 0, 2. This is your 0, minus 3. And these two lines intersect somewhere here. And that point probably will be somewhere. Yeah, if you solve these two equations with an equality sign, you'll probably get the point of intersection. So that will be somewhere like 1.67, comma, say minus some 4.67, something like that. Or I think I've told you wrongly. Yeah, but if you just solve this two, you'll get, so it's probably 5 by 3, your x is, yeah, and y will be, say, minus 4 by 3, something. Yeah. Okay, so now you know how to draw these lines, but still you don't know how to draw the feasible regions. So for that, what you always will do, you'll check the origin. So let me mark this with red. So this is your origin. And now what you can do is that first you take this equation and put the 0, 0 in the left hand side. What we'll get, 2 times 0 plus 0, that's 0, but it's not greater than 0, not greater than equals to 2, sorry. So that means this origin doesn't belong to the feasible region of L1. So the feasible region will be the opposite side of the origin. So you can draw it like this. Yeah. So from the line L1, you can draw it like this. And then let me use another color to denote this. Now you will have origin 0 minus 0 equals to 0, and then this less than equals to 3. The second line will contain the origin, so it will be towards this side. Yeah, so it will be again something like this. So if you notice it carefully, then this blue and this red markers, whenever they overlap, that's your feasible region. So your feasible region will be something like bounded by this part and this part. Okay. So suppose I give you another constraint, which I can put it to green, and probably I'll tell you that L3 or whatever it may be. So suppose I tell you y is less than equals to 0. So it's below x-axis. So whatever you will have, it will be in this region. So here y will be less than or equals to 0 in this case. So ultimately you'll be left with this triangular region, which will be your feasible region. So let me mark it to another color, probably what's left now. Okay, let me pick yellow and shade this region. So this will be your feasible region. So let me write it as, probably it's hard to see, so I'll write it in a different color. So this is your feasible region, this yellow portion. So this is how you can construct your constraint region, and then probably you have to maximize some function in this region, and after that we'll be, I think, able to find out the value of x and y which maximizes or minimizes some function. So this is kind of a constraint optimization problem, or specifically when you deal with linear programs, you will encounter something like this. So that's all about the fifth problem, and something similar to this you will find in your assignment problem, I guess. So so I still have some 5 minutes of my time, so probably I can solve another problem. So that's the sixth problem, and this problem is again a practical mathematical problem that you may have encountered in your class 10th or 12th standard. So it's kind of, suppose, uh, let me give you, I have some sheet having an area of say x and probably x centimeters square or something like that. Then using this sheet, I tell you that you have to like form a jar or something with a square base. So square base, suppose you have to, the base will be square, and then without a top. So your top portion is empty. So it's something like you will have a square base, and then it will probably go something like this, and we'll have the other dimensions. You won't be able to see it, but it's something like this. But you will don't have another square box covered here, so it's kind of an open box. So if you have this dimensions of this base as x naught, since it's a square, this will be x naught as well. And then you will have this height of something like this. So this height will be h. Now you have to find the values of x naught and h so that the volume is maximized and the overall area that you can use is x. So maximize the volume of this jar, uh, find x naught and h. So let me get into the details of this problem. Suppose you have the restrictions of the area. So now you can again find the total area. So you have the area of the base, which is x naught times x naught, which is x naught square. Then you have plus, you have x naught square, uh, or rather it's not x naught square. You'll have the perimeter of this square, so that 4 times x naught. And then if you multiply it with the height, you will get the areas of the sides, and then uh, side surfaces, or should I say, like, and you don't have a top surface. Your top surface don't add up to another x naught squared. So these portions will add up to x. So from this, you can find out h in terms of x naught and x. So your h is nothing but x minus x naught square divided by 4x naught. And now you can have the volume calculated as the volume is V. Suppose now uh, you have the area of the base, which is x naught square times h. So if you put the value of h, you will get x minus x naught square divided by 4x naught. And since x naught not equals to 0, you can cancel this out, and it was there in the denominator as well earlier. So x minus 4 minus x naught minus 4. Something like this, you will get, or I can just write it as, no need to complicate things, x minus x naught, yeah, something like this. Uh, oh, sorry, I have written it wrongly. So let me erase this. Yeah, so this x naught will get cancelled out. We'll be left with x minus x naught squared divided by 4. So now what you can do, you can name it as a function of x naught, and you need to find out the value of x naught for which this becomes maximum. So let me put f prime x naught equals to, when you solve it, you will get x divided by 4, and then you will have this term. So you get 3 x naught square divided by 4. Yeah, I hope I've done it correctly. Let me just double check it. Yeah, I think so. And then you'll have your second derivative, as this part will be 0 anyway. So it's like 6 x naught divided by, so it's 2 of x naught. So since x naught is positive, this is less than 0. So that will give you maxima. So now set this part to be 0. So which gives you 3x naught square equals to x. Your x naught square is x by 3. And that will give you your x naught. It's nothing but root x by 3. And then you still need to find h. So you can directly put this in that equation. So it's x minus x naught square x by 3 divided by, what is there in the denominator? It's 4 of x naught. So you can write it down as 2 times root of x naught, something like this. So one root will get cancelled out. So it's half times, and you can write it as x by 12. Yeah. So this is your answer. That gets you x naught and h. So again, you can have similar practical problems like in mathematics. You probably have already learned these things. So I hope that you will brush up your these little things that you have already known before coming into the class of next week. And I think you'll be able to solve this problem. I think so. You already know this thing, so that's not a big deal for you, I think, to solve. So the challenge of this course will be to solve the assignment questions from week one onwards. So I suggest you to go through the videos of the course instructor before coming to the TS sessions. Uh, I know that assignment deadlines are still a bit far away, but do attend the TS sessions so that you'll be able to answer those questions and solve it pretty quickly. And so that you don't make any mistakes while like doing those assignments and submitting it on time. And please do attend those sessions like from 3 to 4 p.m. And in case in some emergency you cannot attend those class live, do go through the YouTube video link that will be uh, like giving it to you, like circulating it to you, and uh, go through the lecture later as well. So with that, I've almost reached the conclusion of this first week zero class, and I hope to meet you all during Sunday 3 to 4 p.m. this week. And there is another TA for this course. Will be taking another TA sessions from 4 to 5 on Sunday this week. So do attend those, and we'll probably like solving some different sets of problems. So do go through both those courses and sit through those live sessions. That will be very helpful from you, I guess. So yeah, looking forward to meet you all in the next class, and yeah, do revise all these concepts. Thank you all.